In an age when we've mapped the surface of Mars and sent probes to the edge of our solar system, it's almost unbelievable that we've explored less than 5% of our own planet's oceans. The deep sea, Earth's final frontier, remains more mysterious to us than the far side of the moon. This vast, dark realm, covering over 70% of our planet, holds secrets that could revolutionize our understanding of life itself, yet it continues to elude our best efforts at exploration. The reasons behind this startling gap in our knowledge are as deep and complex as the oceans themselves. To truly grasp why so much of the deep sea remains unexplored, we must first comprehend its sheer enormity. The world's oceans cover approximately 71% of Earth's surface, with an average depth of about 2.3 miles. But these figures barely scratch the surface of the true scale we're dealing with. The deepest known point in the ocean, the Challenger Deep in the Mariana Trench, plunges to a staggering 7 miles below the surface. To put this into perspective, if Mount Everest were placed at the bottom of the Challenger Deep, its peak would still be more than 1.2 miles underwater. This immense volume of water presents a daunting challenge for exploration, as every increase in depth compounds the difficulties faced by both human divers and sophisticated equipment. Moreover, the ocean floor is not a uniform landscape, but a complex terrain of vast abyssal plains, towering underwater mountains called seamounts, deep trenches, and sprawling mid-ocean ridges. Each of these features presents its own unique set of exploration challenges, further complicating our efforts to map and understand this hidden world. One of the most formidable obstacles in deep-sea exploration is the crushing pressure exerted by the enormous weight of water above. As we descend into the ocean, pressure increases at a rate of approximately 1 atmosphere for every 10 meters of depth. At the bottom of the Challenger Deep, the pressure reaches an astonishing 1,100 atmospheres, equivalent to the weight of 50 jumbo jets pressing down on a single person. This extreme pressure poses significant challenges for both human divers and equipment. Traditional scuba gear becomes useless at depths beyond about 40 meters, and even the most advanced atmospheric diving suits can only reach depths of around 700 meters. For deeper exploration, we rely on specialized submersibles and remotely operated vehicles, but even these must be engineered to withstand enormous pressures. The effects of pressure aren't limited to the physical integrity of exploration equipment. Many of the tools and sensors we use to study the deep sea, from cameras to sampling devices, must be specially designed to function under these extreme conditions. The development of pressure-resistant technology is an ongoing challenge that continues to limit our ability to explore the deepest reaches of the ocean. While pressure poses significant challenges, it's not the only environmental factor that complicates deep-sea exploration. As we continue our descent, we find ourselves enveloped in an all-encompassing darkness that presents its own unique set of obstacles. Sunlight penetrates only the upper layers of the ocean, with virtually no light reaching depths beyond 1,000 meters. This absence of light presents unique challenges for exploration and study of the deep sea. Without natural light, traditional visual observation becomes impossible. Explorers and researchers must rely on artificial lighting systems, which come with their own set of limitations.
Hey explorers, ready to dive deeper into the unknown? We've got exclusive insights waiting for you. Subscribe to our newsletter now, link in the description. Stay ahead of the tide and never miss a discovery. Now, enjoy the rest of the video.
Powerful lights are needed to illuminate the darkness, but these can quickly drain the energy reserves of submersibles and ROVs, limiting the duration and range of exploration missions. Moreover, the use of artificial light can disrupt the natural behaviors of deep-sea organisms, many of which have evolved in a world without sunlight. This complicates our efforts to study these creatures in their natural state and understand the delicate ecosystems of the deep. The darkness also necessitates the development of alternative sensing technologies. Sonar and other acoustic methods have become crucial tools for mapping the ocean floor and detecting objects in the water column. However, these technologies have their own limitations in terms of resolution and the types of information they can provide. Developing equipment capable of withstanding crushing pressures, operating in total darkness, and enduring the corrosive effects of saltwater is an ongoing engineering challenge. Submersibles and ROVs, our primary tools for deep-sea exploration, must be built to exacting specifications. They require robust pressure hulls, sophisticated life support systems for manned vehicles, and an array of sensors and sampling tools. The complexity of these vehicles makes them expensive to build and operate, limiting the number available for research and exploration. Power supply is another significant technological hurdle. The extreme depths and harsh conditions make it impossible to use conventional power sources like solar panels or air-breathing engines. Instead, deep-sea vehicles rely on batteries or power delivered through long tethers. These power limitations restrict the duration and range of exploration missions, often forcing researchers to make difficult choices about how to allocate their limited time in the deep. Communication with surface vessels is also challenging in the deep sea. Radio waves, which we use for most wireless communication on land and in space, don't propagate well through water. Instead, acoustic signals are used, but these have limited bandwidth and can be affected by various environmental factors. While technological innovation continues to expand our capabilities, the deep sea still holds countless mysteries, particularly when it comes to the strange and wonderful life forms that call this extreme environment home. However, studying these organisms presents unique challenges. Many deep-sea creatures are extremely fragile, adapted to life under high pressure. Bringing them to the surface for study often results in their death or significant physiological changes, complicating our efforts to understand their biology and behavior. Moreover, the vastness of the deep sea means that new species are constantly being discovered. It's estimated that millions of species in the deep sea remain undiscovered, with new organisms being found on almost every deep-sea expedition. This incredible biodiversity, while exciting, also underscores how much we still have to learn about life in the deep. The extreme conditions of the deep sea also make it difficult to replicate these environments in laboratory settings. Unraveling these biological mysteries requires not only advanced technology, but also significant financial resources, bringing us to another major challenge in deep-sea exploration. The specialized equipment required, from research vessels to submersibles and ROVs, comes with hefty price tags. A single deep-sea research expedition can cost millions of dollars, putting it out of reach for many scientific institutions and limiting the frequency and scope of exploration efforts. Funding for deep-sea research often competes with other scientific priorities, including space exploration, which tends to capture more public imagination and support. This competition for resources means that deep-sea exploration projects must often prove their immediate value or potential for economic return to secure funding. The high costs also influence the focus of deep-sea exploration. Areas with potential economic value, such as regions rich in mineral deposits or marine genetic resources, often receive more attention and funding than purely scientific endeavors. This economic bias can skew our understanding of the deep sea, leaving vast areas unexplored simply because they lack obvious commercial potential. These economic considerations not only affect the amount of exploration we can do, but also influence how we plan and execute deep-sea missions. leading us to the complex logistical challenges involved in these expeditions. Unlike space missions, which can be planned with precise orbital mechanics, deep-sea explorations must contend with a dynamic and often unpredictable environment. Weather conditions at the surface can severely impact deep-sea operations, with storms or high seas making it impossible to launch or recover submersibles and ROVs. Even in calm conditions, the process of deploying and retrieving deep-sea vehicles is time-consuming and requires careful coordination. The remoteness of many deep-sea exploration sites adds another layer of complexity. Research vessels may need to spend days or weeks at sea, far from any port. This requires careful planning for supplies, fuel, and potential emergencies. Time management is also crucial in deep-sea exploration. The extreme depths mean that descents and ascents can take hours, leaving limited time for actual exploration and data collection at the seafloor. Researchers must carefully prioritize their objectives and be prepared to adapt their plans on the fly based on what they discover. While careful planning can mitigate many of these logistical challenges, deep-sea exploration often takes place in international waters, adding another layer of complexity to these missions. The deep sea doesn't recognize national boundaries, and much of it lies in international waters. This presents unique legal and political challenges for exploration efforts. The United Nations Convention on the Law of the Sea provides a framework for managing marine resources and conducting scientific research in international waters. However, interpretations of this framework can vary, and disputes over access and resource rights can complicate exploration efforts. Amidst these legal and political considerations, we must not forget the most crucial element in deep-sea exploration: the human factor. While much of deep-sea exploration is now conducted using unmanned vehicles, human-occupied submersibles still play a crucial role in certain types of research and exploration. However, taking humans into the deep sea presents its own set of challenges. Physiologically, the human body is not well adapted to the extreme conditions of the deep sea. The high pressure can lead to nitrogen narcosis, a condition similar to alcohol intoxication and decompression sickness, commonly known as the bends, if ascent is not carefully managed. Psychologically, the cramped confines of a submersible, the surrounding darkness, and the knowledge of the crushing pressure outside can be mentally taxing. Selecting and training individuals who can perform effectively under these conditions is crucial for successful manned deep-sea missions. As we've seen, the reasons why 95% of the deep sea remains unexplored are many and complex. From the crushing pressures and perpetual darkness to the technological, economic, and logistical challenges, deep-sea exploration pushes the boundaries of human ingenuity and perseverance. Yet, it's precisely these challenges that make deep-sea exploration one of the most exciting frontiers of scientific discovery. Every expedition to the depths has the potential to reveal new species, uncover unknown geological features, or provide insights into the fundamental processes that shape our planet. So the next time you look out over the seemingly endless expanse of the ocean, remember the hidden world that lies beneath, a world that, despite all our technological advances, remains one of the least explored frontiers on our planet. It's a world that continues to challenge us, inspire us, and remind us of the incredible diversity and resilience of life on Earth. And if you want to dive deeper into the mysteries of the ocean, make sure you're subscribed to this channel.